Hi, I am Tian Prion and I am presenting problem number 14, jumping for Team Slovenia from University of Ljubljana. Okay, so the problem statement is that we investigate the motion of the jumping beans and that we find dimensions of the fastest and the slowest bean. Now, before continuing with the presentation, I want to show you a video of jumping bean in case you haven't seen one yet. Okay, I think video is not working properly. So after qualitatively observing the motion, we proposed theoretical explanation for this phenomenon. We divided motion into four separate parts, and for each part we are able to describe it using only first principles. So the first part is the ball uniformly accelerating from the top to the bottom of the capsule. Second part is the collision of the ball with the capsule, and by taking conservation of momentum of inertia into account, we are able to calculate angular velocity of jumping bean after collision. Third part is rotation of jumping bean, and this part can be described using conservation of energy. Then there is fourth and final part, again collision, and this time collision of jumping bean with inclined surface. This part, however, has no effect on angular velocity of the ball. After the final part, ball starts rolling again, this time, however, with initial angular velocity. This angular velocity equals previous ball angular velocity after after collision in the previous cycle. So this movement converges, and after the few cycles, all successive cycles are the same. Taking this into account, we are able to calculate final average velocity. And in future presentation, when I'm referring to velocity of jumping bean, I'm actually talking about this final average velocity. Okay, so here is a movement with here is a video which justify our division of. Okay. So before talking about theoretical results, I think relevant parameters, assumption, and approximation should be addressed. Relevant parameters for our model are mass and dimensions of the capsule and the ball. External parameters include are inclination of the inclined surface and gravitational acceleration. For assumption, we said that there should always be enough friction to prevent slipping. And for approximations, we said that momentum of inertia is constant rotation and that energy between collisions, so in rotating and rolling part, is conserved. Here's the formula of this final average velocity, but I don't want to discuss it in depth now. It should be noted, however, that movement is not always possible. And if rotational kinetic energy before rotation is smaller than the peak, than the maximum of potential energy during rotation, so here you can see peak on the graph, then movement is not possible. Okay. Theoretical results. So using formula for average limit velocity, we can see final results gathered from those two contour plots. Parameters of the bean of the ball are stated on the PowerPoint, and velocity is increasing. Okay. Mass and dimension of the capsule are increasing in this direction. On the left side of the PowerPoint, plot presents same peak, same beam, but this time, however, with different scale on the axis. Theoretical results. This problem statement also asks about angle, about velocity's dependence on angle. We plotted this graph, which shows how velocities depend on angle, and as expected, with increasing angle, velocity increases as well. On the bottom side, left bottom side, we can see where movement is not possible, and this is because there's not enough energy for being to rotate in rotating phase. It should be noted, however, that movement is not realistic if angle is too large, and this is the reason for this is it is very hard to provide enough friction and to prevent slipping. Now we can answer the question from the problem statement: what is the fastest beam? As we can see from those graphs, for beam to be the fastest, its capsule should be as light and small as possible. And what is the slowest beam? Well, as we have said before, movement is not always possible. So all beams in the white area for which movement is not possible does qualify. Another thing I haven't talked about is the size of the beam. So what happens if you fix ratios and lengths and just resize the beam? Well, with magnifying it, velocity increases as well. Experiments now equipped with theoretical model. We began with experiments. We made several different beams. For some, we used metal ball and capsule, as stated in experiment, stated in problem statement, and others were homemade. For those homemade beams, we used aluminum foil and marbles. We flipped beam down various inclined surfaces, and here are gathered results. For the bottom three beams, the bottom three beams are made of pill capsule and a ball, and the top three are made of aluminum foil and marbles. We can see that most experimental results match with theory quite well. However, we are still not able to predict exact velocities. We are, however, able to predict which beam is faster, and to predict which beam is faster. Exception is the bottom two beams, and the very bottom beam should be faster than second from the bottom. However, as the difference in observed velocity is so small, we can consider this difference to lie in experimental error. Another experimental aspect that matches with theory is that generally smaller beams are also slower, and the bottom three beams are much smaller than the top three, as their dimensions are way smaller. Okay. Here are the results of experiment when we flip the same beam on different inclinations, and the blue line presents our theoretical prediction. We see that the blue line lies below our experimental results, and the main reason is the slipping. However, as expected, with increasing angle, velocity increases as well. Now, we have seen that our model is not particularly accurate, and we are not able to predict precise velocities. The main reasons are oscillations, jumps, loss of energy, and slipping. On the given video, we can see typical non-ideal behavior of the beams, and oscillation and slipping are the main problem we face. To conclude, we were able to construct a theoretical model, and with theoretical model, we were able to predict which beam is faster. For the fastest beam, its ball should be as big as possible, and its capsule should be as small as possible. And well, for the slowest beam, movement is not even possible. Thus, I think we managed to address the main points from problem statement and get a grasp on physics behind this phenomenon. Thank you.
It's Mateus Laureano Nunes Barbosa. I will be opposing the problem jumping bean. Okay. So first, I would like to address the theoretical model and make some comments on it. On the positive aspects, he recognized that the movement is not always possible. It could have been done with some easier Newtonian analysis based on force rather than on trajectory, and it would be quite more obvious, but he does recognize that through his analysis. He provides an equation for the mean velocity of the beam, although he didn't specify over what he takes the mean, not if it's over angle or if it's over trajectory or maybe time. So, okay, so he can, but on the negative aspects, the ones to improve, he considered the average velocity as velocity, ignoring that it could have some changes there, and that could be a misinterpretation, yet his analysis is still useful, although that's a negative point. He does not address the full equation of motion of the beam. I haven't seen any treatment of that. And the problem with this is we are ignoring initial conditions, right, in not solving the full differential equations for motion. So he does not also consider the differential initial conditions, as I just said. So my suggestion is to analyze the position of the ball bearing centroid as a function of time, which could be done by an analysis based on force. So now for the experimental analysis, in the positive side, he does apply video analysis to minimize human error instead of course, this is very hard to do it another way because you would have a great uncertainty related to the measurements. Another thing is he does not many parameters were analyzed. Just he analyzed the ratios, but it's kind of tricky because we are looking for we don't know if the ratios are independent, if it depends on the ratio or just in one mass or the other mass or one length or the other length. So we could break those up and then analyze more parameters based on that. So he lacks a direct comparison between hypothesis and experiment. The only graph I saw comparing both had 3 points and they were completely off. So that makes me concerned about the conclusions he draw. So he does not have a large enough experimental sample to support the hypothesis. So one thing that I questioned during my questions was how the uncertainty was estimated. So for this kind of problem, I would really suggest that we use statistical uncertainty. Just make the measurement many times, which is possible because you use a video analysis and you can just start by the same initial conditions and then run it over and over again. And then you will have an uncertainty on each point in time and each point in space. So, and that would be useful in this case because then we could have a good estimation, actually good estimation of uncertainty. It is especially good for this case because, especially for the homemade device, it was very ununiform. So it's very appropriate to use this statistical error analysis. So also didn't account to parallax. There was very few about the experimental setup, and depending on the position of the camera, you could mean not actually measuring it. You could have an underestimation of velocity, for instance. And that could even increase the error in graph in slide 10. So my suggestion is to record the phenomenon and use the visual software such as the tracker to plot the beam's position as a function of time, and then you can make further analysis based on that. And of course, as I mentioned, use statistical methods to infer uncertainty. All right, so to be addressed during the fight, I want to address slide 10, which is his comparison between theory and experiment, the uncertainty calculations in experimental setup and statistics, the condition on each sliding occurs, which is very important because his theoretical approach does not take that into account. Slide 3, part 4, I have a little issue with that and discuss the most relevant parameters to be accounted for. All right, so I will stop sharing now. If you could please show me slide 3, part 4. You say that there will be no effect on slide 3. Is that 3 enter maybe? So what you say there is that there will be no effect of in the angular velocity of the ball in the second collision. However, if you play it, you will see that there is a little bit of it hits the ground and then it goes a little bit back. Wouldn't that cause a little bit of wouldn't that be a problem? Wouldn't that cause a change in the velocity of the ball, especially because you are considering static friction, right? Once you are not considering slipping, then the peel going back would actually cause the ball to reverse velocity and restart everything. What are your opinion on that? Hello? I think you're muted.
Okay, sorry, I was muted.
Oh, there we go.
Yes, in non-ideal behavior of the bean, there of course is change of angular velocity of the ball. However, in our theoretical model, we haven't taken jumps into account. I think if there are no jumps, there should be no change in angular velocity.
Yes, but look, if you play the video once again, it should, when in the second collision.
This is example of non-ideal behavior, and our theoretical model is doesn't take any aspect of non-ideal behaviors into account.
Okay, so yeah, so it doesn't take, although we see that in the video that it seems like a relevant relevant parameter. However, you didn't take into account. But I also recognize that one video is not enough just to draw this conclusion. So I would like you to tell me when will sliding happen and when it will be relevant.
When should we take sliding? Can you repeat the question? When should we take sliding into account in our?
Yeah, when is it relevant and when it happens?
Sliding happens if angle is too large, and direct approximation for this angle is tangents of the angle equals k, coefficient of friction, and this is my first approximation.
So for a large friction coefficient and a small angle, it never happens?
But no, if angle is too small, it doesn't happen.
Okay, but one problem then is how the rotation happens, the conservation of momentum actually, because whenever it hits that point, there's no way momentum, that would require an infinity force, which we know to be unphysical. So at some point it will slide a little bit, even in this small angle approximation, don't you think? The small angle condition. Do you agree?
I think it is still able to calculate and propose a model in which there is conservation of momentum of inertia and.
Yeah, I see, but yeah, okay, that was one assumption, but I'm trying to investigate the reasons why. Can you go to slide 10 now?
Yes, slide 10. In general, yeah.
Because your theory there seems not to match your experiment. You see, so I'm trying to point out parameters that you could have considered that would make that graph look better. So I have some issues with that graph that would like to comment.
Yes, yeah, I think the main reason for those errors are slipping, and of course I agree that it is a very good idea to take slipping into account.
Yes.
And one additional improvement that I was thinking about is that we could be measuring angular velocity of the ball rather than normal velocity.
Yes.
And we would just neglected sleeping in our experimental results, not in theoretical ones.
I see.
Yeah,
So another thing is about the uncertainties.
yes, uncertainty.
The uncertainties you calculated for we have an example here. So how did you get those uncertainties, like for the radius or for D, your parameter D? How did you get those?
Experimental errors. Those are
Is that a
methodology.
standard error for equipment?
Yes, yes, because of equipment.
Okay, you know what concerns me here is like your radius, for instance, for your homemade peel, I feel like it would be quite ununiform, right? Because if you've done it yourself, it's kind of like irregular for each shape. So it wouldn't it be better to just make the measurement several times with different ways and then have a uncertainty based on that and not in the equipment? Because that you were saying me, you're telling me that you measure it at one point and that's the radius, but it could be uniform everywhere.
I think our PowerPoint stopped working. Okay, so here's a picture of our homemade beans, and I think the error in their unhomogeneity in their shell is not that problematic. I think there are a lot of different aspects of errors and non-ideal behavior that we faced, and this is not the most problematic one. I think here you can see that it is pretty homogeneous. Error maybe equals 0.1 millimeter.
Yes, but that the fact that this image is even this image even makes me more concerned about that because I see that there is some irregularities in the surface. But anyways, I think we have a potential question from the audience. So Bob, do you want to ask a question? I think you mean slide 9.
Right. So I have a question on slide 9. So you were saying that you were giving a list of experimental results and saying that they are in agreement with your theory. And I was wondering if you could would like to elaborate on that.
What they are elaborate on that. So the difference between observed and proposed velocity is about for most of the beans is about 20% maybe, or even 10. And we are, for all cases except the bottom tooth, we are able to predict which bean is faster. And also our theoretical predictions are like systematically somehow smaller, but not too much. So I think if we somehow taken slipping into account, superposed, and it is a very good idea, the match should be perfect.
How do you have good results here, but in the other graph you don't have such as good results? Could you explain that?
Okay, so those beans are homemade. They have much better results, and I think because they are generally larger and the ratio, so mass ratio is higher. So the error for homemade beans is smaller. Those beans, however, are made of pill capsule and the ball. Yes. And slipping here is even more problematic than for the top three. And this graph is presents beans made of pill capsule and the ball. This is the same point. This is 16 around here, and this is 16 and 9. Okay, so this is 9.
Okay, I see. It also concerns me a little bit the only matches for the ones that had high uncertainty, and also where does the uncertainty comes from? the uncertainty for the velocity in the upper graph.
Measurement. Yes.
Because I asked it for the other measurements, but
No, this is the
we
subject.
don't have much time now.
So looking this graph for both teams. So imagine, no, the one which was already, not the numbers. Was the page 10, yes, exactly, this one.
Right.
Now imagine 10, okay, yes. Now imagine I'm 5 years old and I come to you and I tell you, you say you are complaining, you look, my graph, my points, my graph, they do not agree at all, and they tell you, but it's easy, just to move up the graph, or you move down the points, and you will see the agreement is much better.
Yeah.
Do you think that this difference can be related, you already discussed the sleeping, but do you think these can be related to the problems we already discussed, or there is something else to be investigated? So it seems there is a constant deviation.
Yes.
So just a comment.
Yes, who would you like to start, or may I start?
I don't know if wants to start the reporter. Maybe the
I can-
reporter is.
Oh yeah,
I don't know.
maybe the reporter.
Yeah, maybe the reporter first.
Yeah, I think that as you proposed, we should move the experimental points down.
Yes, in the sense that if you move, you get a better agreement, but you should be allowed to do, in the sense that there is a shift, almost. But
Yes.
is it justified?
Yes, I think the main reason is sleeping, and
Only sleeping? Or do you think that there are other reasons? I don't know, the angles you start, the material of the plank you used to make your beans sleeping, or whatever. I don't know.
So I think I think sleeping, and that difference in distance is constant, as you can see. So for each rotation, there's a constant difference of actual distance the being have traveled. So, and the reason for this is sleeping. So the force, it is the same beam, and yeah, it slips for the same distance down the inclined surface during each period of time, which increases velocity for constant value, or some constant.
I may also provide. May I provide an explanation now? My view.
Yeah.
So yeah. So one thing before answering the question, I would like to point out first that there are only 3 points, so it's very hard to tell if it's actually matching or not.
But I'm
But
5 years old. I'm 5 years old, so for
yes,
me it's
exactly.
enough.
Yeah, exactly. But then, if you think that way, there is a reason, and that is even counterintuitively, sliding is actually faster than just tumbling down. This is because whenever the beam tumbles and it hits the ground, it loses all that energy which was stored in rotational kinetic energy, right? So when it hits, he's considering, and it's actually a far consideration, that it's a plastic collision. It just stays there, and then it loses all that energy. But when it's sliding, it's accelerating while it does that, while it moves. And although usually sliding makes it actually goes slower, sliding in this case is still accelerated, while this thing reaches a kind of terminal velocity. So it still increases, but at very, very low factors. So it reaches a potential terminal velocity there. So that's the one reason why I think this would match.
Okay.
I would just
It's
like
okay
to.
for me.
Okay.
May I ask a question, please?
Yes, can Stanislav ask a question? Could you clarify, please? My question is to reporter.
Yeah.
Does your average velocity in your analysis depend on the initial position of a beam relative to inclined surface?
No.
Or it doesn't depend at all?
Because it is initial velocity. I can, I think.
Not initial velocity, but you can
No, okay.
place it vertically or horizontally.
No, it doesn't. It doesn't.
It doesn't depend.
It is the limit cycle. It is the average velocity of the limit cycle. And
I don't understand. Could you beam simply rotate along the axis relative to axis of symmetry as a wheel?
yes, okay, it can. But then, yes, okay, I investigated only this typical movement, which I considered interesting. Otherwise, just normal rolling of the ball and cylinder down in flat surface. And yes, that in this case, movement would be completely different. And I think velocity would be higher. But if we are talking about this final limit velocity, the position of the beam, so position if we put capsule horizontally or vertically, has no effect on limit velocity that we predicted in our theoretical model.